Log on, tune in, find out. Another good idea from Cambridge.
Here's Dave Higdon. Dave's a research scientist at Los Alamos National Lab in their statistics group, former group leader. He's a very prolific researcher in computer modeling and simulation modeling. So that
I am going to get the long introduction.
you are, and I will also say that Dave is also a new fellow of the American Statistical Association. Right, so apparently anybody can get into the club. Anyway,
That's true. I've brought the overall level down, that's for sure. All right, Derek, thanks. So originally it was supposed to be one of my colleagues who was going to talk about an application. So this is kind of a cheat because it's really a statistician talking about an application. So every now and then you'll really see that I'm a fraud here. Basically, this is a project with a number of physicists, cosmologists, computer scientists on emulating the nonlinear dark matter power spectrum for the universe. I'll tell you what that is in a second. But basically, it's a big computational campaign to do these large-scale simulations of billions of particles, billions and billions. Yes, it makes me sound like a physicist now. Lots and lots of particles that are evolving under gravity and under slightly different cosmologies to see which ones look like the universe we've got here today. So lots of large-scale computational effort here. I'll talk about the tie to physical observations, although this effort really is more on just the simulation campaign, but it does tie to observations, and I'll talk about that as well. And the statistics will be fairly minimal, so even though that's supposed to be my gig, right, I will only show you cartoons, so no real formulas. And if there are any hard questions, you can ask Derek about it. He'll get that. All right, so what do I know about the universe? Well, you can go on Wikipedia and stuff and figure that out. But 20 years ago, it was fairly uncertain about what was going to be the fate of the universe. We go back to, what was it, 1920s? Hubble takes some observations and people figure out that the universe is expanding, and that leads to this Big Bang theory. And so here we've got a bunch of Big Bangs happening. And up until 20 years ago, people really didn't know that after the Big Bang, everything's coming apart, but gravity's acting on the universe, right? So no one really knew was the universe eventually going to come back together into the big crunch at the end? So that's sort of that first picture there. Was it going to keep expanding? Was it going to keep expanding at a linear rate, or in fact, is it going to expand at an accelerating rate? And so it turns out this was an open question up until about 15, 20 years ago. And it turns out that the answer is over here on this one. The universe seems to be accelerating at a faster and faster rate. And if they've looked at more observations of other objects farther and farther away and looking at how fast are they moving away from us, they're moving away at a faster rate than the things that are closer. So now the verdict is in, and the universe is definitely going to expand forever. So the heat death sort of end of our lives will happen, but that's billions of years away, so we don't have to sweat that too much. All right, and so if you look at models for cosmology, there's no model that has an expanding universe in it or accelerating expansion of the universe. And so they've added this term called dark energy. They think there's this vacuum energy going on in the universe, which in fact is causing the universe to expand farther away at when the universe gets less and less dense. This is when that force is acting more. So it just acts at a constant rate per density and or per volume, and as a volume gets less and less dense, it becomes more of a factor. So it's only a factor in the later universe as things have expanded and gotten less and less dense. Oh, it's the wrong way. Yeah, we also go backwards in time sometime as well. Watch out for that. Talk may never end. All right, so now a statistician will talk about cosmology, so bear with me for a second here. All right, so 14 billion years ago, Big Bang happens. And we can, if we look back and do the microwave collection, we can actually see small fluctations in density at very early times. So the cosmic microwave background lets us look at that. And you can see real slight fluctuations in the matter density in the early times. And then what happens is this slight fluctuation is just going to be evolving over time according to gravity. And eventually enough stuff will accrete and will form some of these first protostars that happen. Those things will actually start igniting, spitting out other elements. And then we'll start forming the stars that we see in our sky today. And so if we go on to about 14 billion years, here we've got a sky that we can look out and see. So there's the physical system. The Big Bang, sort of unknown initial conditions, but we know about how to describe the fluctuations in density. And so what are we trying to do in the computational world? What we want to do is initialize a box that's going to be like a universe. We want to initialize it with fluctuations that are like that cosmic microwave background density that we see here. So we start with some fluctuations that are like that, and then let this thing evolve over time according to, well, the rules of gravity. So our good Newton Institute thing here. Gravity's big. Also, there's a number of other cosmological factors that might influence how this thing's going to evolve over time. So one of the things is just how much matter is there in the universe, what it's made out of, and also things like the Hubble constant, which is basically just the rate of expansion. But that other thing I talked about before, dark energy, that's also going to be important here. That if we put in a lot of dark energy, then it means that things are going to accelerate apart more quickly than if there's not a lot. And dark energy is not going to affect the early universe much, it's going to affect the later universe a lot more. So dark energy will affect things, the rate of expansion, the Hubble constant will affect things, the relative makeup of the universe. Let me see if I have that here. No, so I'll talk about that real quickly. So it turns out the universe is made up of baryons, so that's the stuff you and I are made out of. Turns out about 4%, or maybe it's 0.4%. As long as you're within an order of magnitude, it's okay as a statistician in cosmology. Small amount of baryonic matter, the stuff that we are, the stuff that we basically know about. About 25% or maybe 20% is dark matter. This is stuff that we don't know what it is, but we can infer that it's out there, but mostly by watching motion, say, of a spiral galaxy. If you watch a spiral galaxy turn over time, watch it move, then it doesn't evolve according to just the equations of gravity for the things that we can see. Clearly, there's a lot more matter there, so there has to be a lot of other massive non-interacting particles in these galaxies moving for it to move the way it does, the way we see it. So you can infer that there's some sort of dark matter that way, but none of the particles that we know about are candidates for dark matter. So it's something else. So it looks like there's more matter there than we know about, but we don't know exactly what it is. So things like the Large Hadron Collider are one of the things that I'd like to be able to do is maybe they can see particles that might be candidates for what dark matter actually is. You can also see dark matter indirectly. A lot of times there'll be these images that you can see on the web of gravitational lensing. So a distant object, you'll see it twice because there's some intervening mass that's bending the light around in two different ways. So there's other indirect evidence for this dark matter. So dark matter is not very controversial. But by far the majority of the universe, according to this standard cosmological model, is this dark energy component. So if we look at the universe, it's in three chunks basically: baryonic matter, dark energy. And by far the most dominant part is dark energy, which explains the rapid expansion of the universe in later times when it's less dense. So, so things that control this simulation is the relative makeup of these three components, the rate of expansion, the Hubble constant, and maybe a few other things that tell you about how you observe the universe, things like a spectral index or something like that, or an opacity. So there's a few other parameters that involve our observation of the universe. But basically, if we fill in a universe, put in a certain amount of dark matter, baryonic matter, dark energy, seed it with some sort of fluctuations that look like what we see in the cosmic microwave background, put in a Hubble constant and maybe a few other things, we can basically evolve this thing until it looks like, or until we got to 14 billion years. And hopefully your simulation runs faster than the actual time that it took to get there. It turns out they run almost as long, but not quite as long as that. And so what we want to do is we want to compare this sky to this sky and ask what are the parameter settings that give us a sky here that looks like the one that we see when we physically observe it. So basically that's a calibration problem. All right, so how do we do that? Well, all right, now it gets less and less exciting, but here's what we got. So the data we're going to look at comes from the Sloan Digital Sky Survey. So this is a telescope in my home state, New Mexico. And what it does is it looks at lots of things, but if you put it together right, you'll get sort of circles of information like this. And so All right, so here we are in our little galaxy, right? It's this spiral thing. And so we can look up from our galaxy and we can look down. But if we look sideways, we look through our galaxy and we really can't see anything. So if we look at, what do we observe? We tend to observe two disks or two wedges of the universe. And that's what we see up there. So our observations are basically going to be something like this. So this is, usually these are clusters of galaxies or galaxies themselves. I think they're clusters here. And so it has this kind of a webby structure, and that's from gravity acting on the universe over this long amount of time. You tend to get lots of voids and strings of things together. And what we can do with a simulation is put in the parameters for our cosmology, and then we end up with a box that looks like this. And so boxes, what's easy to do with a box of particles is we can just look at a density map over this cube. And then we can take an FFT and basically get a matter power spectrum. So for one of these boxes, we can get a power spectrum for the density, and that's what these gray lines are, subject to some transformation, basically a power spectrum density. Now there's a whole separate field that takes observations like this, and this is just one of probably hundreds of these sorts of observations that come from the SDSS telescope. If you put them together and spend a career, you come up with these black lines here. So the crosses are where the data points are. So these are points on the power spectrum that are consistent with these observations. And then the error bars are about 2 sigma uncertainties, 2 STs. So going from the raw data to this thing is a lot of effort. And so, and the reason why it's hard is exactly why it's easy over here. If you have this complete data set, doing the power spectrum is not too bad a thing to do. It turns out doing the power spectrum when you have incomplete data is tough. And so not only do we can't see through our galaxy in certain directions. If there's something light in front of you, you can't see beyond that. So a lot of it's about estimating what you can and can't see, and so what fraction of the universe are you actually seeing? And that's why you get lots of uncertainties here. All right, so it's just important to realize that, okay, so this is as a function of wave number. So over here we have things that are separated by large distances. So this is very sort of large scale sorts of things over here when k is small. And then as the wave number gets smaller and smaller, you tend to be talking about things about shorter distances. And so spectra are looking at averages over the whole universe of things of differences in short distances. And that's why you tend to have a lot less uncertainty for the larger k than you do for the high k. But maybe the interesting structure might be much more at this lower k, at these sort of larger wave numbers or these larger distances at the smaller wave numbers where this larger scale structure is more important. Okay, so physical data there, and it turns out these are just about independent. And they're not quite, but for practical purposes, I think they are. And so we run these things at different cosmologies. We'll see a bunch of different spectra, and that's what the gray lines are. I think there are maybe 37 different cosmologies. If we have time, I'll tell you why it's 37. Okay, so 37 cosmologies, 37 gray lines, there's data there. And what we want to do is, well, the goal of doing these big chunk of simulations there is to figure out what parameter settings are consistent with the observations that we've got. Going backwards. All right, and then here's the design. So we're varying 5 different parameters here: a spectral index, Hubble constant, another spectral parameter, and then the amount of dark matter and the amount of baryonic matter. And so these two are going to determine the amount of dark energy just by default. And so what we tried to do was get a space-filling design in these 5 dimensions, but it turns out our initial design wasn't in these variables. It was in a transformed version of these variables. And so we worked really hard to get a 32-run design that was space-filling in a transformation of these dimensions. But then after the fact, the cosmologists really thought, you know what, we think this parameterization describes it better. And so if you look at this thing, there's a, so this cross-section here, which is also the same cross-section right up here. If you look at this new transformation, we had these blank, it was like a football going through the middle, and then we had blank parts on the corners. And so with 5 more runs, that was all we could afford. They took about a month, a little over a month per run. Where do we want to put them in for these last 5 in order to try to make this more space-filling? So yes, space-filling Latin hypercube design for some other transformed version of the parameter set that we're looking at. And then we untransformed it and thought, oh my goodness, we better do something to fix this up. and threw a few more in there. So that's how it ended up working out for this example here. So these simulations were pretty long. All right, statistics. Here we go. So what we have, here's sort of a cartoon of the thing. You can think of that k, the wave number, being here, and the parameter value being here. And so usually we'll standardize the parameters when we're computing to live between 0 and 1. And so I guess I've done that here as well for the wave numbers. And then the model output is on the z-axis here. So basically the model will take any input setting for the parameter and wave number and spit something out. Actually, it spits out a whole set of spectra as a function of wave number, but don't worry about that just yet. And so basically these dots are like our suite of simulations. Here it's only 20, so we've got 37 in the one that we've got. And what we're going to do is we're going to fit a statistical model over the simulations. We'll use a Gaussian process. That seems to work pretty well for this example. And so these things will basically interpolate the model. They'll work well if you have lots of smoothness, which we do. And you can also say what's your uncertainty about predicting what the model would say at places you couldn't afford to run the model. All right, so there's sort of the emulator problem. That's really the main focus of this application. But then if we can go ahead and put this thing together, now we have observations at different wave numbers, say. And maybe a priori we've got a uniform distribution over the parameters. And then what we want to do is constrain those uncertainties for the parameters and say, well, what parameter settings are consistent with the data that we have. So I draw this picture to kind of explain the methodology. Almost never does it work out that, oh, there's some parameter setting which is consistent with all the data that you have. Almost never. Except here it's not so bad, and that's because our data just aren't quite good enough yet. So yeah, so we'll have to reinvent or have to alter the standard model for cosmology soon. And then just to go with that, then is just this sequence of pictures that. All right, so here's the too good to be true sequence, but now what we're also adding is a term that accounts for discrepancy between what your model would say and where reality is. And so it shows up here in the equation-wise that we'll have a discrepancy term, which is maybe just a function of wave number, plus our observation error. And so here we have this extra thing that we're estimating, but if things are good, we'll estimate this discrepancy to be 0. And then if you look here, I think I'll just tweak a few of the, like 2 of these data points and get us to a spot that's not quite as good. And then if there is no setting that does go through all the data, well, now you're going to have to make choices somehow about, well, what do you want your model to do? What setting, which data should you try to match to have your parameters mean something here? And so that gets a lot trickier. Luckily, we don't have to worry about that in this case. All right, so we have a response surface model. And then I'll just say real quickly, we ended up using a basis representation and fit Gaussian processes on the weights that go with the bases, but basically Gaussian process model. And then we can go ahead and do a sensitivity analysis. Now that we have this emulator for what the computer model would say at places we couldn't afford to run it, we can go ahead and look at questions like, if we take the spectral index parameter here and vary it over its range, how much does that change the matter power spectrum? Not much. And so what's the big thing here over this range that we've looked at? Well, it does look like the amount of dark matter is affecting things the most. And realize that when you change the relative proportion of dark matter, you're also changing the relative proportion of dark energy. So certainly that's not unexpected that that's the biggest driver. And the amount of baryonic matter, since it's so small, even if you change it, it's not going to have as much effect as the dark matter is going to do. So really the relative composition of the universe is the stuff that seems to be driving the model output the most. All right, oh, so we better, 5 minutes, all right. All right, so if we were doing a calibration problem, we could go and ask, all right, well, what parameter settings, now using our emulator, seem to be consistent with the data here? And basically here's a representation of this 5-dimensional parameter space that's consistent with the data. We do get about 0 discrepancy here, and there's a little bit. And then we can go ahead and make predictions someplace. So we can use this idea to go ahead and do the inverse problem. But really what we're focused on here is the emulation problem. And so if we take one of our simulation outputs, so here's one of our high resolution outputs, What we get is a matter power spectrum that looks pretty smooth most of the time until you get up to these smaller wave numbers. And that's just because our box is only so big, and when our distances corresponding to a wave number are fairly large, about half the box size, well, then we don't get lots of replication there. And so we tend to get a lot of noise at the low K. All right, so that's just sampling noise. Our cosmologists will call it, that's just cosmic variation. So that's cosmic variation now instead of just sampling noise. All right, so what happens is we have a lot of uncertainty up here. We don't get a great estimate of what the spectrum is from our simulation here, and that's just because the box size is limited. We can put in more particles and make a bigger box, and we'll have to pay a big price in computation to be able to do that. It turns out where it's really important is right around here in this wave number, where you see some acoustic baryonic wiggles and things in here that are important. And also it turns out for the very large wave numbers, if you think of evolving this just system of particles over space and time, just evolving it over time, that at really large distances, things are fairly linear, meaning that you can get away with a linear model, meaning that you can infer what the spectrum is for a fair bit of this thing until the nonlinear interactions or the real smaller distances really creep in with that 1 over r squared gravity law. So it turns out that we'll be able to get around that part. Okay, so here's what we end up doing, that we have one sort of month-long simulation at the highest resolution, biggest box we can afford. And then we also have a number of 4 sort of slightly lower resolution things that take about a week each. And then we combine that with 16 fairly low resolution simulations. And what goes on here is that, well, here are these low resolution ones, and you end up with this biased estimate here towards the bottom. And that's because that box isn't big enough. Oh no, we don't have enough particles to get this, to get the large wave numbers about right. So it starts biasing because there's just not enough particles in the simulation. Okay, but up here where we see lots of noise, all of these simulations are about equally accurate. So we can combine things here to help beat down the noise up in these higher or lower wave numbers. And then we just threw these ones in for good measure, but they're going to have the same properties. They'll just be a little bit longer before they fall off here in terms of bias, and they'll certainly help beat down some of the uncertainty here and be a little more accurate as we get into this nonlinear regime as we go smaller down here. So the idea is to combine these simulations at the different resolutions because they have different they help us in certain areas, but we have to know where the bias creeps in and where we can use linear theory to help put this all together. All right, so here's the usual picture for the log of the power spectrum. It turns out that just because we wanted to see things, we just did a slight transformation. And so we just do subtract a constant out of this thing that they like. And now we look at these simulations. So this black line here is the high resolution simulation. We're going to trust it up here. We know our box size and number of particles we have is going to give us accurate numbers up here for this higher K. Here it's having the extra numbers of simulations going to help us estimate this power spectrum better, just because we have 16 rather than just 1. And then down here where we see lots of noise, it turns out that's exactly where the linear theory kicks in and does well. And so here basically we've got the linear theory. It's very accurate as long as our wave number doesn't get too high, and that means the nonlinearities aren't kicking in. Up here we're going to use the fact that we've got 21 simulations here to help combine information, and you can see these baryonic acoustic wiggles that are important here pretty well. So it's important to get those things. And then at the end, we're just going to start trusting the high resolution simulation here for the large K. And that's a good place to trust it because that's where you get lots of replication. So the cosmic variance is beat down. And the fact that our box is big enough and we have enough particles, we're not going to get the bias up there. All right, so here's how we combine all these different resolutions. So it's not an emulator combining the resolutions. It's just kind of thinking about it and picking off which pieces of the different resolution simulations are going to help you in different parts of the estimation here. Real briefly, we just want to, it turns out that you want a lot of smoothness in some places where there's lots of averaging and not much smoothness, or a lower bandwidth in other places to model this thing. And so we end up doing a non-stationary model that changes the bandwidth as a function of where you are along this wave number. And it turns out you want not a lot of bandwidth here if you're going to recover these acoustic wiggles. And so the bandwidth goes down here, but it goes back up here, and certainly it's fairly high there as well. Oh, we're not going to show statistics, forget that. And so in the end, here's the estimated bandwidth we have for this process that's being modeled, that the bandwidth goes down here where the wiggles are, and then it goes back up to something fairly large as we get out to the larger K parts of the simulation. So basically, we've got these 37 simulations here, and what we want to do is put those all together now and estimate an emulator for all these things. And oh, yeah, lots of model checking. Is it getting the variance about right? Is the model error about right? And those things all checked out pretty well. Very, very normal looking. It looks like the model assumptions are doing pretty well here. And then so now this thing is actually an emulator that a lot of the cosmologists are using. So we have these 37 very high fidelity simulations. We have some 4 times as many slightly lower fidelity simulations. And then on top of that, times 20 low fidelity simulations, all combined to make this emulator so that different people can use this thing, put in different cosmologies, and figure out what the dark matter power spectrum is going to be. All right, I'm basically done, but I'm going to take 1 more minute anyway. All right, so I use that here. We use that here in this cosmological application. We looked at simulations, physical observations, and constrained parameters. There's other simulations here, implosion experiments, where we do a very similar sort of thing here. So it has a number of applications that we can use this for. And one of the things I just wanted to throw out here is that we use different resolutions in a way that was very well tuned for what we were trying to estimate. We just knew that this simulation worked well up to this wave number, that simulation was good over here in this wave number. Then all of them were equally good over here where I needed to beat down the variance by replication. In other places, dealing with resolution ends up being a fair bit harder, and ocean modeling is one. So here's an ocean model for at least the last generation of IPCC sorts of runs, that it was at a resolution where here's what an ocean looks like, say, for surface temperature. If you run it at a higher resolution, you see stuff like this. And it turns out this is really important, especially for climate feedbacks, because this is transporting energy in ways that are a lot different than this model's doing. And so how the ocean's going to take up heat, distribute heat, maybe move it down to other temperatures is going to be important. And so getting these effects right, even in a cruder resolution simulation, is important. How to do that ends up being fairly hard. So exactly how to do that, we're trying all sorts of experiments, and that turns out to be a rough thing to really figure out, or to get the right sorts of behaviors. And then another place where this multiple resolutions or bridging scales is important is in material science. That you can do these simulations at sort of quantum level, and you might be able to put in impurities, but maybe you can only simulate a few hundred, maybe a few thousand atoms or molecules in here. So you're putting this thing all together. What you'd really like to infer is, if I put some extra iron in this material, how is that going to change the strength property? Something that's very much a bulk measure. And so going from sort of this microscopic or atomistic scale to these bulk properties is what people want to do in material science. Another application of bridging these scales that is rough. So now I'm going to end it there, and thanks for humoring me.
When you talk about the different resolution simulations, when you said you got 4 medium resolution, are they 4 runs of the same simulator or 4 different simulators?
Yeah. So they are the same simulator. They're basically different initial conditions. So there's this cosmic microwave background, which is described pretty well by a Gaussian random field, or the log of the density is described well by that. And basically, they're just different realizations of this field that you start with.
Okay, so how do you decide you're going to do 16 low resolution, 4 medium?
I went away on a trip, I came back, and there was a plan. And it wasn't like I really had a better idea about what was going to be enough. It was sort of what they thought they could fit in there. And I think maybe in hindsight now, but I wouldn't have known this going in, it's as good as anything, is I'm not sure that the extra work for the mid-level resolution ones were really that much worth it that much. We beat down cosmic variance here, we had the same amount of bias here. So it only helped us a little more in connecting the linear to the nonlinear part of the theory, but we think the high resolution one did almost as well. So going back to that one, this is always how I end up doing experimental design is, well, I don't really know, pick something. and then at the end we can kind of think about, oh, this would have been smart, but I don't think I possibly could have thought of it going in. But I think, all right, having done this a few times, now once in a while I feel like I have something useful to say on the design part. But I think it's been tough for me in a number of these.
So she took my question. But what about the fact that you're conditioning, you have your initial conditions for that one simulation? Like, how are you being able to account for the fact that that's a pretty strong conditioning statement?
Yeah, so I can only predict your future if it was initialized just like this, right? So, so it turns out that, so you can kind of look at it in this picture. So first of all, we're only looking at the matter power spectrum. So we're only looking at something that isn't hugely influenced by that starting initial condition. And so it turns out for things at large wave numbers, meaning small distances, it's very insensitive to the conditions. So a lot of this stuff isn't going to matter. It's where this fuzz starts creeping in relative to how good your data is where it's going to start being important. And if you remember, the data is pretty uncertain at the very small wave numbers, meaning for the large distances. And if we look ahead to, what are the next probes coming out, they're mostly going to push things down this way, not up that way. So it's going to be hard to get a much broader swath. It'll be slightly broader, but it's not going to knock things down all that much at that very high end. So what that ends up meaning is most of the data we have is living out here, which isn't quite as sensitive to that. And then the other thing that kicks in at the very small wave numbers or large distances is that linear theory, just lots of linear operators just moving this system around is pretty close to being accurate there. So that also is impervious to the initial conditions as well.
On a serious question, I have one small.
Oh, I think we have a serious one. Then we'll get to you.
A serious question.
So I might have missed it. Did you mention what the 37 cosmologies were about?
Yeah, so it started with 32, and it was because we did this design that was in a transformed version of the parameters that we started with. So what do we want to do? If you want, the general idea is that for these Gaussian process models, if you can fill the points in your space well, that the emulator you build will be pretty accurate across the space. And that's basically the goal that we're after. But it turns out, after doing the runs, we changed what space we wanted to fill. And so we did the first 32 runs and said, no, that's not the right space, it's this space. And we looked at the design projection in this new space, and it was missing a few corners. And you can really see that if we try some cross-validation. We hold out one sample and ask, well, how do we predict with an emulator built on everything else? It does really well, except for these 2 points that are in the 2 corners that we're kind of missing. And if we take out those guys, well, now there's nothing nearby for that prediction to get it well with. And so, yeah, if we did it all over again, I would know that too. So yeah, so it's usually these things I worry about rather than what's the right number of these relative amounts of simulations. Did I do something really stupid? And more often than I'd like to admit. Is this still being recorded?
Oh, yeah, on a serious question, it's good. I wonder if your colleagues could assure me that there is one Big Bang. I think always something of the Big Bang. And if we were in billions and billions of Big Bangs, future and present, that might explain some acceleration.
Yeah. All right. Yes. All right. So that's a good point.
Sure, there's just one.
Right. And you're talking about many over the course of the universe existence, not
well, I don't like
necessarily
the word
many
una,
universe.
but we're terribly small. Maybe it's a whole soup of Big Bangs causing acceleration.
So the model we're using, the standard model for cosmology, clearly is conditioning on one Big Bang. And so the simulations that we have in there are assuming that model.
Not billions and billions, okay.
Yeah. So yeah, there are alternative theories which you could try to do something like this with. I imagine simulations for many Big Bangs that could show up in random places, or you have to figure out where they're going to show up.
Well, if you're in the soup of these things, you'd see the acceleration perhaps.
Yeah, that's a good question. But no, for this standard model, it's not in there. I mean, they have the cosmic inflation part, which is just sort of pre-programmed. Yeah.
I'm too old to die young, so don't care that much. But still, it's.
Yeah, so I can't help you with that. So it's possible. No, we just worked with the one big bang gang here.
Yeah.
I'm going to chime in with a question. So on some of the projects that project where I'm dealing with, got this multiple resolution sort of model thing going on, and it's not obvious that the higher resolution models are better than the lower resolution models in predicting certain features of reality. Do you run across this, and did you run across any of this with this kind of data, or is it?
So, not for these, particle and cell sorts of simulations that we're taking lots of particles and just evolving them according to gravity. So here, a particle really represents a cluster of galaxies. Here, not so much. I think there's a whole separate piece that's looking at. So it's not really quite proper to take these dark matter simulations and compare them to what you observe, which is not going to be dark matter. It's going to be baryonic light matter sorts of things. That there should be some sort of translation from dark matter to what we observe. And in there, these resolution issues do creep in. So, so here, not so much. But maybe other people out here might have more experience with that. But certainly in other applications, yes, a coarser, lower resolution model seems to do better, which you can show, well, mathematically it's not doing better. So whatever's going on mathematically is being more than accounted for some other type of effect. So it's got to be some sort of balancing errors that are in your model that are going on one way or another.
Any other questions?
So you've got this, as far as I understand it, the problems with the almost like wavelengths to the left of your plot, and this noise there, and then things get more accurate down that end with the high fidelity simulation. Do you use any technique like multi-grid in computational fluid dynamics, where you can start a fine model and then interpolate to a coarse model, improve things on one scale, and then go back to the fine and so on?
So for this type, so I didn't tell you much about the simulation, but this was a particle and cell simulation. And so what you do is you get these particles in a big box, and you don't really solve, the gravity equation with, you look at the distance from every other point in the thing. Well, it's billions of particles, right? 2048 to the third particles. So it's a lot in there. And so what they end up doing is, so the particle and cell strategy says, let's chop this whole thing up into a grid, and at each grid point, I'm going to estimate about how much mass I get. And then if you're on a grid, you can solve this Poisson or this distance equation, all these distances using an FFT. And so they use that to do all their work. And so it means that the way they're doing sort of the low resolution or the high resolution stuff is by making this grid small and just making sure you have enough points so you're not biasing things by doing this FFT strategy. So there are other strategies for doing these big n-body simulations that are, more tree-based and things like that. And yes, in those cases, they will often try to refine these things and get better accuracy for the smaller distances where it's important to get that. It's well known that for these particle and cell methods, they don't do well if you try to adaptively refine the mesh. And so it turns out that they like to have one uniform mesh for these things, and maybe do slight strategies about weighting, about how you combine a local sample to assign to your grid point. So it's just because of this particular simulation style that, no, they don't want to do adaptive resolution. Other ways of solving this n-body problem, yes, they do.
I think that'll end the session. Dave will be around all week, so we can track him down if you have more questions. Thanks again.
All right, thanks.